Okay, we're going to talk about convection today. And so that is the third of the three main ways that heat energy is moved from one place to another. So we've talked about radiative transfer, talked about diffusion, and convection is sort of the general term for the remaining way that heat can move. And it also is a way that other material can move as well. So, for example, understanding a little bit about convection can help us understand the atmosphere, large-scale atmospheric patterns, ocean circulation, plate tectonics. So it's a big topic that I wanted to cover. So what do we mean by convection? So we're going to describe it as movement of fluids due to density variations in a gravity field. So this is actually this is a real central theme here. Okay, so when things have different densities, there's different forces that are acting on them if they're adjacent to each other. Something with less density and something with high density, and when you're in a gravity field, which we are on planet Earth, the less dense things are going to want to move up, and the more dense things move down, right, to release some potential energy. And let's be clear here. By fluids, I don't mean liquid. I just mean anything that assumes the shape of its container. So obviously gases and liquids do that, but we'll be giving the example of the solid Earth, the mantle, which can also act as a fluid on a long time scale. So the density variations generally are due to two different things. One of them is temperature. So, of course, as things get hotter, the molecules are bouncing around more quickly, and they take up more space. So you have the same amount of matter with more space, so you have a lower density. So if the temperature affects the density, and also the composition, of course. And both of these are important for different things that we'll be talking about. So, for example, water becomes more dense when it's saltier, and when it cools down. And both of those matter for ocean circulation. So some of the examples that are relevant for Earth science are ocean currents, tectonic plates, which are closely related to mantle convection. There's still debate about, what's driving the plates, how much of it is related to the deeper motion of the mantle, and how much so the plates drive that, and vice versa. But in either case, it's convection that's what's happening. And then, the wind, formation of clouds, and also sort of planetary scale atmospheric patterns. All right, so a classic pattern that convection takes is an arrangement into what we call cells. And so for the example of the atmosphere, and at the end of this video I'm going to link to a nice illustration of in a tank with some water that's been dyed. You can see these things happening, and this happens on your stove when you heat up water to boil it. But starting with the atmosphere example, so the top. This comes back to our discussion of electromagnetic radiation. At the top of the atmosphere, radiation is losing energy. Energy is being lost into space due to electromagnetic radiation. Top of the atmosphere radiates heat into space. And so the top of the atmosphere is cooling. And the base of the atmosphere, so at the surface of the land, that's where the sun's energy, a lot of it, is being absorbed. So there we have heating, and you probably are thinking back to the diagram showing, the balance of electromagnetic radiation and the greenhouse effect. So this sets up a situation, and we talked about that there at that point as well. The less dense warm air moves up. The cooler air sinks. And the way that this organizes, the hot and the cold air don't really mix exactly. They don't move through each other so much as they move around each other. So we could say this: the currents don't move through each other, at least at a small scale, but they form cells. So we get, if we could draw this, we have hot, and this is just like on your stove, right? So stuff heats up, moves up, pushes things out of the way that are up here. And as the warm stuff is moving up, it is cooling down as it gets closer to the edge, and radiation into the air or into space, depending on what system you're in. So it starts to get dense as it moves up there, and eventually it gets so dense that it heads back down, right? So we form these convection cells. And so continuing with the atmospheric example, we'll look at a couple scales. So thermal columns, and this came up as well when we were talking about the greenhouse effect. So as the air heats and rises, and I should say there's generally a somewhat uneven distribution of the sun's light. For example, there's clouds or something. Some area has a different albedo. It's going to warm up more than the other areas, and that's where you're going to have the thermal columns happening. So the air heats and rises, and that air cools, and as it does so, it holds less water. The cooler air is not able to hold the water. The water condenses, falls out, and you get thunderstorms. So this is the scale of several kilometers where we have like the land surface, and you get these big sort of towering clouds in the rain coming out of those. So that's sort of at a kilometer scale. And then at a much larger scale, at the planetary scale, we have something called the Hadley cells. Let's see if I can write that a little bigger. Hadley cells. And the Hadley cells are just one of, I think, 6 different sort of belts going around the planet. But they're sort of the easiest to describe. So in this case, the heating, which is stronger, so let's say solar heating, is the strongest at the equator, right? That's where the most solar energy reaches. And again, the air warms and rises. You have quite a bit of rain due to that for the same reason. And this causes, if you look at if you just pull up Google Earth and look at the planet, you have this belt. This is the equator. You have a zone, and I have a green pen, so it's sort of this is where you have a lot of tropical rainforests. There's a lot of rain because of this. And so let's just write that down. Causes equatorial green belt, we could call it. I don't think that's an official term, but and then again, that air, which is now dry, comes down eventually, typically at the tropics. And here we have, I should say, little rain, and we have deserts. Okay, so if we kind of look at the side here, we have air coming up and then coming back down. And so here we have this belt of deserts. If you look at the map of the globe, you'll see sort of a brown zone, right? And that's sort of the area where this air that had lost most of its moisture on its way up has cooled and it starts to come down. And so in both of these cases, actually in all of these cases, for convection, the motion is from high pressure to low pressure areas. This is for all cases, okay? Not just the atmosphere. So this is worth trying to underline. So if you think about heating the material increases the molecules are pushing harder, right? So it's like if you heat up a balloon, it'll get a little bit bigger. So it's increasing its pressure. All right, let's move to an example of the oceans. And again, we touched on this a bit when we were talking about the carbon cycle. So the ocean's water moves around, and about half of that is due to wind. So wind drives around 50% of circulation, which is interesting, right? So the interaction of the convection of the air has this effect on the motion of the water as well. So that's about half of the cause for water moving, and we know this because computer models you can just like turn off the wind, right? So the other half is the other 50% is what we call thermohaline. So thermo being temperature related and haline being related to saltiness, basically. So in other words, temperature and salinity affect density, water density, significantly. And salt water is denser than fresh water, and that's because basically if you have your water molecules, salt can just kind of fit in the space between them, so you can get more material in the water, and it turns out to be denser in the case of water. And So as you might expect, the dense, salty, cold water sinks, and this tends to be at high latitudes, so near the poles. So why is so cold makes sense, right? You know it's colder at the poles. But dense and salty, so it's dense and salty due to two things. So due to high winds can evaporate the water molecules, and which causes the water to get saltier. And sea ice formation also takes just takes hydrogen and oxygen out, right? And it leaves behind more water, and that water gets saltier and saltier as a result of both of these cases, just taking out hydrogen and oxygen. Let's say because of evaporation and sea ice formation. Okay, so this is a general pattern. This can happen anywhere, but the overall pattern is there's sinking, and we looked at this before. We saw in the North Atlantic, especially, there was a lot of water, of this deep water formation due to this effect, and so as a result, so if water is sinking near at high latitudes, it needs to come up somewhere else. So this is offset by water rising elsewhere. And let's draw an illustration. So we're at the equator. Here's the pole, and here's our ocean. So the wind tends to be blowing the water from the warmer areas near the equator towards the pole. So I should have said this earlier in the atmospheric part, but on the scale of the planet, we have it's hotter, cooler, and this is a lot like heating the convection cells. You could think of in a different dimension, right? So that it's both like moving up into the air and coming back down, but it also is a tendency for the hotter material to want to move towards the poles as well. So that tends to the winds tend to blow warm water northward, and then as that water starts to get saltier and sea ice starts to form, it sinks. And then to balance this, it comes up more slowly everywhere else. And this has about around 1,000-year time scale. The typical water molecule might take 1,000 years to go through this rotation. And so this over here, just to be clear, I was talking about the atmosphere. So these fluids, the water and the air, anything that's undergoing convection can transport other things. So we can think of it as like the water is moving. The water itself is moving. The salt in the water is moving. This is very different. This is a distinction from like the electromagnetic waves, right? Where it's like, or water waves, right? So it's the energy that's moving with the waves, and the material tends to stay put, more or less. So here it's the whole body moves, whether it's a certain amount of water or air, and so then it carries with it everything in it. So it carries its energy. The energy moves, just like radio, like the electromagnetic waves. The energy moves, but also the material moves. So we call, when we're focused more on that motion of stuff, we call it advection. And there's some, if you look into the terminology, different fields sort of use advection and convection sort of interchangeably, or have slightly different definitions. So I'm just going to say advection is closely related and synonymous with convection. But we're really focusing with advection, at least in earth sciences, on the transport by bulk motion. Often with the mean fluid flow. And so this is different. Often with convection, we're talking about the density differences driving it. And here we're just saying, okay, well, the stuff is moving, and what happens as a result of that motion. So when this happens, the properties of a substance, and I'll give some examples. For example, temperature are generally carried along, get a free ride. So an example is silt in a river. Okay, so gravity is causing the water to move downhill, and silt is caught up in the water, and it's just carried along by the water flowing. It's not really about density variations. It's just that the silt's in the water and the water's moving. Ultimately, the water is there probably because of some, the things we talked about. It's the atmospheric patterns in circulation. But if we're just kind of looking at the river, at the bank, we see the silt being carried in the river water. And another example of advection is advection fog, it's called. So here we have, let's say we have a warmer region and a cooler region. And so this will be the surface of the Earth, little tree. So if we have airflow from the warmer region into the cooler region, the cooler air can't hold as much moisture, and a cloud will form. So the fog forms. So the moisture in the air is advected from one region to another, just as part of some bigger atmospheric flow, and causes a phenomena, this fog to form. So this is sort of, advection is sort of just like it's a side note, really, in this conversation about convection. But just something to be aware of. It's another term that sometimes gets used, and I think sometimes it's synonymous with people are using it synonymously with convection. But in earth sciences, it tends to be more in this definition. All right, so we're going to finish with a final example of mantle convection, and we'll talk about both the overall motion, but also what is going on that allows solid rocks to move. Look at a little bit of detail at that. So solid rocks in Earth's mantle behave as a fluid over long time periods. And it's worth emphasizing that Earth's mantle is solid. Okay? So a lot of times this is a common misconception, but if you look at a cross section of the Earth, there is a liquid inner core, liquid outer core. But that's the only predominantly liquid part. You've seen diagrams of this like mantle convection, and it might be one layer, it might be two layers, it might change from place to place. And the reasons for why there may be one or two layers are not well understood. And the same thing goes actually in the atmosphere. There's, like I mentioned, the Hadley cells. But it's a complicated explanation for why the circulation in the atmosphere and in the mantle breaks into multiple cells, potentially. And for the mantle, we're not even sure exactly to what extent that's the case. But in any case, the mantle is convecting, clearly, mantle, and it's a solid. Okay, so a lot of times people see it, and it's colored in introductory textbooks as red a lot of times, so people think, oh, it's just this big liquid zone, but it is a solid. And it will partially melt sometimes, and that's where a lot of magma comes from, but it's 90 some percent solid. All right, so kind of like the other examples that we gave, the Earth's surface is cooling, it's losing heat. And so the rocks that have been at the surface, they sink at subduction zones. And just like the example for the water, the density is controlled both by the temperature and the composition. So this is review from 106, but even though the continents are cold, their composition is less dense, so they don't sink. But the ocean lithosphere is buoyant when it's hot, and especially dense when it gets cold. So it's specifically the ocean lithosphere that sinks. And we could draw that same, I've drawn this here as well. So it's the stuff cooling down, and it sinks, and the warmer stuff comes up, right? It's the same for the atmosphere and the oceans. Okay, but so what's different here is that the Earth's mantle is solid. So I want to talk a little bit about that. So this motion, we're not used to thinking about rocks being able to flow, accommodated. So that motion is accommodated by various processes. Including, and this is the one I want to talk about because it's related to a recent topic, diffusion. So there's something called diffusion creep. And this is one of the main processes that allows the rocks to move. So all crystals have defects. So we're going to zoom into sort of the molecular level, right? So if you have a crystal lattice, and this could be anything, could be a diamond, quartz, metal, they'll have imperfections in the lattice, lots of them. So we'll call this this is called a vacancy. And the reason that there's vacancies is, well, one way to think about it, it's a thermodynamic thing, but basically if you have a boundary between nothing and a crystal, we talked about diffusion of heat and of matter, but there's also diffusion of like nothingness, right? So it's just thermodynamically more stable to introduce some vacancies into the crystal. And so we're going to just kind of wrap up here by talking a little bit more about diffusion creep. It turns out that the concentration of vacancies, we'll call it X, is proportional to the exponent of this is like a stress term that we're not going to worry too much about, but it's inversely proportional to temperature. So in this form, this Arrhenius form should look familiar from the diffusion segment of the class. So as the temperature goes up, the number of vacancies goes up. And that's because of the negative sign and the fact that the temperature is in the denominator. So higher temperature, more vacancies. And if you look at a grain, it could be a grain of some mantle rock. For motion to happen, like the grains need to change shape, and so what will happen is the areas. So let's say this grain is being stressed in this direction; it's being squeezed. The vacancies will move. So you'll have areas with higher concentrations of vacancies, and then there'll be motion from those areas to areas with less concentration, and the overall effect of that will be for the grain to change its shape. And that process allows sum up the total of trillions of little grains changing shape that allows convection to happen. And this is called grain boundary diffusion. And it follows basically the same rules as the other sorts of diffusion that we talked about, including having a form, this Arrhenius form that we saw for the temperature dependence of diffusion constants for materials. And they can also move through, let's change these arrows just to be a little clearer. They can also move through, the vacancies can move through the crystal, and that we call volume diffusion. And the rate of motion is proportional to the flux of vacancies. That sort of makes sense, right? So the more of these, the faster these can move, the more of them that there are that can move, the faster this change of shape is going to happen. And that's proportional to this Arrhenius term. Where we have some, what's called an activation energy and temperature. And I wanted to come to this because it's something we also talked about. The illustration of this is something we talked about back with Daisy World. The idea of like sort of, this is, in this case we're literally talking about a sort of energy we can measure on the y-axis, and we're talking about the motion of some thing. In this case, it's like a vacancy, or it's a molecule in the crystal lattice, and it's kind of bouncing around, right? And there's a certain amount of energy that it would require to send it flying over to the next place it could be. And that is what we mean. That's the activation energy, that term. So the rate of motion is proportional to the flux of vacancies. So this really is another way of saying this, is it's proportional to the number of molecules with a certain kinetic energy. That's what the Q is. A certain amount of energy that could allow them to move to a different state. So got into a little bit into details related to solids, but I wanted to do that just because of some of these connections with things we've talked about earlier. In particular, this form, or this general idea of different states and a certain amount of energy that's needed to allow a change to happen. That we saw this coming up in terms of the motion of grains, the change in shape of grains. We saw it with the same equation coming up, the same form, the Arrhenius form coming up when we're talking about how quickly can a titanium molecule move through a quartz lattice, or an iron or magnesium molecule move through a garnet. It's related to the temperature, and it's specifically related in this form because it's a matter of saying, let's say you have an iron. You have an iron molecule. This thing could be like an iron molecule, and it needs to, in order for this thing to change shape, it needs to move to a different place. So if we turn up the temperature, it starts bouncing around a lot faster, right? And it's more likely to be able to move. And so it's both a function of how hot it is and also how tall is this peak. How big is that Q? It's that ratio. That's what matters. And we also kind of, is more of an less quantitatively, that came up as well with when you were talking about the stability of different states of a system. How we could be in a case where we're in a very stable system. In that case, the peaks are very high, and it's going to take more of a disruption to move something out of its state. Or we could be in a case where these peaks are just barely there at all, and then in that case, like a disruption could be relatively minor and cause a big change. So I'm gonna wrap this up with coming back to the bigger topic of convection. And if you're watching this on YouTube, there's a link to a different YouTube video I'd like you to watch that just sort of illustrates the convection. And if you're looking at the Dropbox file, that'll just be the next thing you see.